Hello, my name is Steve Reiser. I'm at the University of Washington. I'm going to talk about profiling float technology in the GO-BGC array today. I'd like to thank my sponsors, the National Science Foundation, as well as NOAA and NASA, for funding GO-BGC and SOCOM and a number of other related experiments. You can see there on the left three different kinds of profiling floats. We have an Argo Apex float. This is what's mostly used in the Argo that we use in core Argo. A BGC Apex float. This is a version of the regular Apex, but is longer with more buoyancy and has, as you can see, more sensors at the top. And then a BGC Navis float, which is larger yet. The two yellow floats, the components are built by Teledyne Webb, and we do the assembly, checkout, and programming in our own lab here at the University of Washington. The BGC Navis is built by Seabird Scientific. This is the Argo array as of a few days ago, and GO-BGC is very closely tied to Argo. A lot of what we're going to be doing in GO-BGC comes directly from lessons we've learned in Argo. And so I'm going to just say a little bit about Argo, that Argo began in 1998. There are now 32 countries contributing. There's global coverage of floats, including the Antarctic sea ice zone. The data are all publicly available in near real time. Since 2007, there's been at least 3,000 floats operating at any given time, and now there are over 2 million profiles of temperature, salinity, and pressure collected as part of this data set. And here's an important one. Over 4,000 scientific papers have been appeared in refereed journals since 1998 when this began. So Argo has made a very large and important contribution to ocean science. And as well as there have been over 300 PhD dissertations written based on Argo data. This is an example of what Argo has given us. This is the change in temperature as a function of depth as a global average from 2007 or 2005 or so, when Argo first started having a significant number of floats, to the present. And you can see here a continuous warming here, that the ocean is warmed by something like 0.2 of a degree near the surface, and as much as 1/10 of a degree or a little bit less than that below the surface. So here between 0 and the surface and 1900 meters, you can see a steady warming here. And this is, of course, important information for climate models. It tells us something important about climate change, and this is a uniquely Argo result, which we wouldn't have had unless we had this large array of floats in the water. And you can imagine that over time, 10 years, 20 years from now, we'll be able to do the same kind of mapping and averaging and looking at the anomalies of the biogeochemical variables that are going to be measured as part of GO-BGC and BGC Argo. This is a map showing the current distribution of BGC Argo floats in the world, and there are now about 400 of those. The recommendations from the BGC Argo implementation plan from a few years ago was that all these floats should have 6 sensors. That's a CTD, oxygen, nitrate, fluorometry and backscatter, pH, and a radiometer. Most of the floats shown on this plot do not have 6. They may have 1 or 2 or 3. But we're working towards that. These floats have been deployed by many different countries. The first 11 GO-BGC floats out of our array of 500 just went in 2 months ago, and they're this group right here, and they're performing well. And I'll say some more about the data from those here in just a moment. So there are several different kinds of floats we use in, or we're planning to use in GO-BGC. The left if we look at these two floats on the left here, we have an apex float, the components manufactured by Teledyne Webb, the assembly and checkout and sensors are installed at the University of Washington and at MBARI. These floats all have nitrate, pH, a CTD, and oxygen, and then on the bottom here you can see the fluorometer and backscatter sensor, and there's also the iridium antenna here. In GO-BGC, we're going to deploy 500 floats over 5 years. About 40 per year will be done by UW and MBARI of this variety. The other variety on the left here is the BGC Navis float made by Seabird Scientific. It has many of the same sensors configured in a somewhat different way. The buoyancy engine on this float is a bit different, but in the end, these two floats do very much the same kinds of things. About 40 of these per year will also be made, or will also be deployed by the University of Washington and Woods Hole. These floats are built commercially, so anyone can buy one of these. We simply cannot make enough of the UOW and MBARI floats. We're maxed out, so we need another supplier, a commercial supplier, and that's why we're working with Seabird on this float. There's also a float that's largely used in Europe, not much in the US, but is a perfectly good float is the NKE Provar float with BGC sensors, which I show here. Our European colleagues are using these, a lot of these, and they're doing a fine job with those. There's one other float that will eventually be used in the US, is the new BGC Solo float. This is made jointly by Scripps and MRV Corporation, and as you can see here, this looks very much like what we're used to here, the other floats. It's based on the Solo design that has been a very important float in core Argo and has worked really well, and this is a variant on that. Here's the NCAP, the first one of these that just came through the other day. My colleague Sarah Perkey at Scripps supplied us with this. And the first test of these will be deployed in the Pacific Equatorial area later this year, late this year. Eventually, we hope there will be 10 or 20 of these per year deployed as part of GO-BGC. I'd like to talk here about how a float actually cycles, whether it's a core Argo float or a BGC float. This is how a float might actually work. So if we begin here at number 1, float is on the surface, its bladder is fully extended, it has its maximum buoyancy. The oil is pumped out of the bladder, and I'll show you what these bladders look like here in a moment. When in doing so, the mass of the float doesn't change, but its volume decreases, and so its density goes up, and the float will sink from position 1 to position 2, its park pressure, which is around 1,000 meters. And then it will stay at that pressure and drift passively, pretty much passively for 9 days or so, until it gets to number 3. At number 3, the bladder will be pulled in yet a little more oil pumped out, and the float will sink to position 4, which is 2,000 meters. That will take several hours, and then at position 4, the bladder will then be once again pumped full of oil, and that will cause the density to decrease of the float, and the float will ascend from position 4 to position 5, which may take 6 hours or so, and that is where the CTD and BGC profile data are collected between positions 4 and positions 5. Presently, we are collecting CTD data at a frequency of 1 hertz. Oxygen is in some cases similar to that, and then nitrate, pH, and FLBB are typically about 100 points of data collected between number 4 and number 5. not evenly distributed, more points concentrated near the surface. Once the float gets on the surface, then it does several things, as you see there. It will get the antenna will be above the water line. The float will get a GPS fix so it knows where it is. It will upload all the data that it's collected to an Iridium satellite. It will collect some in-air samples of oxygen using the oxygen sensor, and this allows us to calibrate the sensor on each profile. And then it will also download any commands. These are two-way communication is possible here. So if we want to change the float mission, we can set up a command in the lab. The float will get the command and change its mission there as well. All of these things together require about 20 minutes of time on the surface. And here's what the data look like. I'm going to show you data from a float here where the red star is. That is GO-BGC float 19129, and there's its WMO ID if you want to look it up. And this is profile 5 from a few days ago. This was deployed in late April. And you can see there on the right what the data look like. We have nitrate, oxygen, temperature, salinity, fluorescence, and backscatter. I haven't shown pH here, but we have that as well. And you can see the discrete points there where the data are collected, but in addition to that, we have temperature and salinity are collected at about every 8 centimeters and then been averaged into 2-meter bins. So there's quite a lot of data collected on each profile. This is how a float actually works. At least the Apex floats, this describes them. There's a motor that that turns a screw. The screw then pushes a piston down. The piston pushes hydraulic fluid in a tube out into the bladder, and then causing the bladder to inflate. And when that happens, the mass of the float is not changed, but its volume does change, and so its density changes, since density is mass per unit volume. And on the right here, I've shown you just in the lab what this might look like. On the top is the case with no bladder inflation. There are actually 2 bladders there, an air and an oil bladder that are sandwiched together. It looks like just one. In the middle there, I show what happens when the oil bladder is fully inflated. We can get about 260 milliliters of oil in that, which is enough to get it from 2,000 meters to the surface. And then on the bottom is where both the oil and air bladder are inflated. The air bladder is useful very close to the surface to make sure that the antenna on the float is well out of the water so it can transmit to the satellite, but it only is effective very close to the sea surface. Here's a bit more theory about how these floats might work. If density is mass per unit volume, we can rewrite the mass in terms of the volume and density. Since the mass doesn't change over the life of the float, then the mass at any given time, we'll call it rho, and v is the same as the mass we began with, which is rho naught and v naught. And those things have to be equal. The other thing we can do is see how the mass changes by differentiating the mass so that dm is equal to d rho v, and that's rho dv plus v d rho, and that has to be equal to 0 since the mass is conserved, that is dm is 0. And so you can rearrange that to see that the relative rate of change of the relative change in density is the same as the relative change in volume of the float. They're related just with the difference being a minus sign. So reference to where we began either way. So combining these two things, we get that the relative change in density or the relative change in volume is composed of 2 things here. The first one there, delta VB over V0, is the change in due to the bladder, and the rest of it is due to the change in the hull itself through thermal expansion and compression. Well, we can measure all these things in the lab, and that's been done here in this table over, and the important parameter here is over on the right-hand side. And you can see different kinds of floats here have different values of delta V over V, and that really determines how deep can we get with these things. So 40-inch aluminum apex, that's a typical core Argo float. The number is 0.0148, whereas a carbon fiber apex for BGC sensors is more up around 0.153. The Navis is 0.192. And the new BGC Solo, it's not built yet, but it's projected to be a number here greater than 0.025, which is bigger than any of the rest of these. So why do we care about this? This is a map of this parameter delta V over V that's required for a float to sample between 2,000 meters and the sea surface. If a float doesn't have a large enough delta V over V, it won't be able to make it to the surface from 2,000 meters. And so this is just a map of that constructed from Argo data. And you can see at high latitudes where it's orange, pretty much any of these floats have enough delta V over V to do that. As we get into the subtropics and then into the equator, the restrictions are much higher because the water is warmer, the deep water is just about as cold, so the amount of buoyancy change necessary to get to the surface is much more at low latitudes here. In fact, remember some of these floats were 0.14, 0.15, and that suggests here that at the surface, or near the equator, we're not going to be able to make it to the surface with those, and so we'll have to choose something else. And this is one of the reasons it's nice to have several different models of floats. Some will work near the equator better than others, and with what we have available here, we're able to do most of the world, and the new BGC Solo is going to be likely the best of any of these. Notice that we don't have anything in the Arctic here, but the number for the Arctic is really severe. It's over, certainly over 0.02, and probably a bit, quite a bit more than that. And it's because in the spring, there's a huge freshwater cap in the Arctic. So a float could typically get from 2,000 meters to 5 meters, but it can't get from 5 meters to 0 meters, just because the buoyancy requirements are so large. And eventually, there will be floats that can do that. Hopefully, BGC Solo will. When that happens, there'll start to be a lot of profiling float work done in the Arctic as well. Right now, there's not too much going on there, but it's a place where we'd love to be able to get more data and observe more things. It's a very important region. The CTD itself. This is a CTD made by Seabird, the Seabird 41CP. Almost all of the floats built since the beginning in Argo in 1998 used this CTD. Over 15,000 floats have been made since Argo began in 1999 with this. The CTD has changed a little over the years, but not too much, and it's been very reliable. A few hiccups, but mostly reliable. This is what the CTD looks like. And you can see here, if we look at the on the left marked intake flow, water enters there. It's pumped in by, near the bottom there, you can see something labeled CTD pump motor. That basically sucks in water as the float is ascending during its ascent phase. The water passes through the temperature, passes by the temperature sensor through the conductivity cells, so we get a temperature and conductivity measurement, and then out through the other side through the exhaust. In doing so, it moves through the biocide tubes, and we'll talk about that in a moment here. So the way this float works is it measures the electrical conductivity of seawater, and conductivity is known to be a function of salinity if you know temperature and pressure. So it's taking the function, the conductivity as a function of temperature, pressure, and salinity, and inverting that function so you get salinity as a function of temperature, pressure, and conductivity. And as the float is rising, it's sampling at about 1 hertz, which at the rate of rise is about every 8 centimeters. That's a lot of data. The data are binned at 2 decibar intervals. That says bars, it should be decibars. The CTD can operate from 0 to 2,000 decibars. Accuracies here about 2 millidegrees in temperature. We hope for 0.01 in practical salinity units and 2.4 decibars in pressure. The pump here, the CTD pump motor that you see, is shut off within 3 meters of the sea surface. So basically the CTD stops collecting data at about 3 meters. And that's to keep surface dirt and biology and film and scum and all kinds of other things out of the unit, because it will clog the conductivity cell. The lower diagram there shows the conductivity cell, and you can see the cell has a diameter of about 1 centimeter. Measuring the conductivity is like measuring the resistance, the electrical resistance in this cell, and if there's any coating in there at all of biology or films or anything, it will change the electrical resistance and the conductivity and give us erroneous salinities. So it's important to keep that clean, and that's what the biocide is designed to do, is to kill anything that might grow in there. So this is just a summary of the communications. All of the data are sent back using Iridium, whether we're talking about core Argo floats or BGC Argo floats or GO-BGC floats. All of our floats now use Iridium communication. The beauty of that is we have two-way communication, so we can change float missions. The transmission speed is pretty good. It's 300 bytes per second. It uses circuit switched data and an Iridium modem, and we have a dedicated server in our lab to receive the data from this. And you can see here how much data we're actually getting. This is just a histogram over a bunch of profiles here over several years, and you can see typically we get about 100, something in excess of 100 kilobytes per profile transmitted. That includes ocean data as well as engineering data on the float. The typical time to get a GPS fix here is several minutes, typically 2 or 3 minutes to get a GPS fix while we're on the surface. And the total time to transmit all the data here is on the order of 10 or 12 minutes, 600 or 700 seconds typically. So all told here, we're on the surface about 15 or 20 minutes per profile to do this, which is a big improvement over the old Argos system that took between 8 and 12 hours. One of the things these floats can do is operate under sea ice. We've been doing this in a program sponsored by the National Science Foundation and NOAA called SOCOM for a number of years now. And SOCOM is very closely related to GO-BGC. The floats are essentially identical, except the SOCOM floats have ice avoidance software on them, which works quite well. There are now over 19,000 profiles collected under the ice in wintertime in the Antarctic, which is an incredible database, which is helping us to really understand a lot more what's going on in the ice zone. You can see there the circle on the left labeled under ice profiles shows what you typically get under the ice in the wintertime. The plot here, the black and white plot, shows a number of profiles from that orange region there. You can see typically there's a mixed layer that's between 80 and 100, 120 meters thick or so. That mixed layer, the temperature is between minus 1.83, 1.86. That's very close to the freezing point of seawater. And we can actually watch this evolve over the winter. We can see it change in the spring and then get back to winter conditions in the fall. The other orange circle there, labeled Float 5300, is a float that in the Weddell Sea that worked for a number of years. One of our early floats, but it worked. It worked very. And this is an example of the data from float 5300, or WMO 5901734, if you prefer. Through almost 4 years of data, and you can see during the time the float was in that orange circle here. If we look at temperature, you can see it's kind of starts out in light purple, then it gets darker as it gets colder, and then around March in 2009, February and March, the ice melts, the temperature increases to numbers that are about -1.5 degrees C. That persists for a couple of months while the ice is gone, and that lasts again up until February of the next year, when once again there's ice melts, we get warming. You can see in all these cases there's a mixed layer here about 120 meters deep, and then there's a third winter there where it happens again, and almost a fourth one towards the end of 2012. And when you look at salinity, you see something very similar. There's these episodes where the salinity gets very low when the ice melts, between times when the salinity goes up due to brine rejection from the sea ice above. Here you can clearly see parts of 5 different winters being exhibited in this float. And a similar thing with oxygen, and we have, of course, floats with all the other BGC variables as well. But you can see with oxygen, when the ice melts, the dissolved oxygen in the mixed layer goes up as the water is in contact with the atmosphere, and at the same time there's also phytoplankton blooms that generate a lot of oxygen. Then over the course of the year, the blooms go away, the ice reforms, the oxygen goes down, and then it happens, repeats itself again the next year at the end of the ice season. So what about the energy required to do all these things? How much energy are in these floats, and what can we do? This is just a table that shows all of the different uses of energy in floats. And you can see here that the major uses of energy here are, these are ordered by amount being used, are the buoyancy pump, the nitrate sensor. Of course, the buoyancy pump would have to be the largest one, because when that pump comes on, it's pumping against 2,000 decibars of pressure, and it requires an enormous amount of energy to inflate that bladder. The ISIS is the nitrate sensor. It's on all the time to keep the optical unit warm. The 41 CP, of course, is on all the time during ascent, and it requires a lot of energy. And then transmitting to the satellite requires a lot of energy. The other things on here require less. The APF9 is the electronics that controls the whole float. You can see the Durafet pH sensor doesn't use much, neither does the FLBB or the Optode. And the last one on here is self-discharge, which is just, if you don't do anything to the batteries, they will slowly discharge on their own. And so altogether, we're using here about 19.8 kilojoules per profile. If you add up all the energy in all the battery packs, we have about 5,200 kilojoules available. So just dividing one of those numbers by the other suggests there's enough energy here for about 262 profiles. That agrees well with our experience with deploying these floats over a number of years. Note that the BGC sensors require only about a quarter of all the energy. The rest is devoted to the buoyancy pump, the CTD, and satellite communications. So BGC is a good deal here. It doesn't use too much energy in general. Here is a plot that shows the performance of these floats over the years. The blue line here is all of our Argo floats going back to 2007 that were never in ice. So they're that's kind of the control. There are 474 of those. And you can see here that the 50% line is out around 260 profiles. So over half the floats are lasting more than 7.3 years, which is really gratifying. We're not the only group doing that, but the fact that we can do that means that Argo is healthy, and we can keep the array going and healthy over a long time. The green line is floats in the ice. You can see they seem to fail a bit more. The ice is tough on them, but even there, half the floats are lasting around 220 profiles or so, which is, again, about 6 years or so. The red line here is our SOCOM floats, which are identical to GO-BGC floats. Many of those are in the ice, and you can see that they look something like the green line, but around 150 profiles, we tend to lose a lot of them. This particular batch was subject to a problem with overusing the batteries, and I think we've got that technical problem fixed. So the hope in the future is that the red line and the green line will look more alike, which means for GO-BGC, maybe we'll get something around 240 or 250 profiles in general out of these, which is close to what the energy budget says we ought to be able to get. So we think we're doing pretty well. We could be doing better here without this battery problem, but I hope we've got that fixed, and so all will be well. So finally here, I just like to finish up with some useful review papers. Here are 4 papers I've listed that contain a lot of references about floats and float technology for people who would like to know more about this. Lots of references here about floats and sensors. I haven't said much about sensors in this talk because the next talk will devote a lot of detail and time to discussing each of the sensors. I've been talking more about how the floats work, and these papers will give you some more information about that. So to summarize, BGC Argo is underway, and GO-BGC is a real beginning towards BGC Argo. BGC Argo calls for 1,000 BGC floats with 5 or 6 sensors in the world ocean, and thanks to the National Science Foundation through GO-BGC, we're going to be able to supply 500 or half of those. The U.S. will be working on that, and that's great. And of course, each of those BGC floats is also an Argo float, and makes GO-BGC an important part of one Argo, which is Core Argo, Deep Argo, and BGC Argo together. Profiling float technology has developed a lot over the last 20 years. I'd say it's in a mature phase right now. We have a good set of sensors. They all generally work. The technology is evolving all the time. There may be even a revolution in technology someday, but for now we're in a good place with slow incremental improvements. GO-BGC, as I mentioned, is going to produce and deploy 500 floats in the global ocean over the next 5 years, which is half of what is required for BGC Argo. And we're depending on the rest of the world to step up and deploy the other 500 floats. GO-BGC floats will be a combination of UW and Barre Apex floats, Seabird Navis floats, and Scripps MRV BGC solo floats. Those floats will be the first test of those will come this fall. And all the GO-BGC floats will have a CTD, oxygen, nitrate, pH, and FLBB sensors. Eventually, we will have a radiometer on most of these floats as well. And the point of this workshop, or at least one of them, is that we want people to use all that data. Just as CTD data has led to 4,000 papers in Core Argo, we are confident that The data produced in GO-BGC will lead to a similar increase in our knowledge of the world ocean and biogeochemical parameters. In order to do that, people have to use the data. And that's what this workshop is all about, is to say, here are the data we're going to get, here's the characteristics of these floats, and here's how to get that data. And that's really the focus of what you're going to hear about on day 3. Thank you very much.